pi button. Actually, I'd use the arc cosine -1 button.
Wait, what?
Arc cosine of -1 is pi.
Oh, interesting.
Now, we have a relationship here then between this angle in radians and how far you are moving around. If my angle is 2 radians, I've gone 2 radii around. If I've gone 2.5 radians, my arc length here is 2.5 radii. So the arc length is going to be equal to how many radii I'm going around the outside times the angle in radians. So this is in radians. I sort of think of this as SRO, even though it's a theta, standing room only. If you have trouble remembering, but we have S equals R theta. Now, if we look at the units, and this goes back to something that was said earlier, if we look at the units, what would be the standard unit for arc length? Go on,
S.
away from Bueller.
S.
For arc length? Length?
Sorry.
Eva?
Meters?
Yeah, meters. So if that's in meters, what about a radius? What would be a standard unit for radius? Like you mean it.
Meters?
Like you mean it.
Meters.
There we go. So we get meters is equal to meters times radians. So the only way this works is if radians is equal to 1. So I sometimes will refer to radians as a unitless unit. It is actually optional whether you actually write radians or not. Thus, a student I had a number of years ago decided to tack radians onto the end of every single answer.
Oh no.
It's not technically wrong. However, if I don't have to write it, why would I write it ever? Well, if I was saying that I had an angle of 5, did I forget to write degrees, or did I mean 5 radians? And so you write it for clarification. So I would write 5 radians, even though if I wrote the angle is equal to 5, without any units there, it's assumed to be radians. But just to make sure that there's no question about it at all, whether it was just sloppiness or I really meant what I wrote, you would write radians, or rad for short. So, with that relationship right there, we're going to extend it. So if I'm talking about something traveling around in a circle here, the arc length is basically the distance that was traveled. So if S equals R theta. So if I'm looking at something traveling along a distance here, then the distance traveled is equal to the change in R theta. I know the radius isn't going to change, so that can factor out. So I'm left with the change in distance is equal to R times the change in the angle. If I divide by time, so how much time it took to do that, well, over here, this is distance divided by time, otherwise known as
Speed. Or in this case, velocity.
no, speed, distance over time,
Then why'd you write a V?
because that's the symbol for speed. Without the vector symbol, v without the vector symbol is
Wait,
speed.
what? It is?
Yes. Now
That
you
might
know.
explain some confusion.
That could quite well be. And over here, I have the change in the angle over time. So this is known as angular speed, and the symbol is an omega. It is not a W, it's an omega, lowercase omega. As sort of a 70% rule, when you deal with rotational motion, you tend to use Greek letters. So we have a relationship here between V and omega, how fast this thing is rotating. The SI units of omega would be radians per second. In everyday speak, our typical units are RPMs. That's typically how I see it. Okay, questions up to here?
So
This will come
theta
back.
divided by time is omega?
Yeah, change in angle.
Okay.
Typically, we just do theta over time. It usually put from context, whether the angle they're talking about is the angle that something moved through or an actual position, angular position. Now, if I take a right triangle here, this angle here is theta, and we'll just do,
Can I ask you a question?
yes,
You know when we're doing force diagrams and you do the same kind of W, are those also omegas?
no, those are W's.
So you just write them the same?
No, that's my W, lowercase w.
Oh, with a little
That's my omega.
line.
Yeah, I got the flare to off to the right,
Okay.
the serif, I guess it would be. All right,
Okay.
so if I have an angle here, this is, we'll just call it A and B and C, Pythagorean theorem. Or I know that the sine of theta is A over, the opposite of the hypotenuse, A over C. If theta is small, B and C are practically the same length. Because C is going to be, if I have a circle that's a radius 1, that would be 1, and this would be something really close to 1. This would be something really small. But in this, we get the sine of theta, therefore, is approximately if theta is small. So if theta is small. The two less than symbols means much less than. If theta is much less than 1, then, and again, talking radians, then sine of theta is roughly equal to the same as A over B, which is just the tangent of theta.
Are you making up that double thing as much less than, or
No,
is that like a math?
That's what my professors use.
That's a math rule?
It's a physics thing, I assume it's a math thing.
Well, that's what
I got it in physics.
Or,
Now we can go one step further in this, in the fact that, who's had calculus,
do you know what it was related to?
Maclaurin series, Taylor series, sorry. Maclaurin series or Taylor series? Not ringing a bell? Okay. It turns out that sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and it all. Not a particularly convenient way of solving for sine of theta on the calculator, but it is going to help us in our particular situation. Yes?
Is that on the bottom, like 3 to the power of 1?
No, 3 factorial is 3 times 2 times 1, 5 times 4 times 3 times 2 times 1. As a side note, cosine of theta is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus 1. So if theta is small, much less than 1, well, if I square it, it's going to be even smaller. If I cube it, it's going to be even smaller. So if theta is really small, then these terms right here become insignificant. And what we end up with here is that sine theta is approximately equal to theta in radians. So, this is the small angle approximation if theta is much less than 1, then the sine of theta is approximately equal to the tangent of theta, which is approximately equal to theta, assuming in radians. Stephanie?
How small is small?
Hopefully I have the right notebook here. I don't seem to have it with me. I'm just gonna let that run, and I'm going to
Grab, hopefully, the right notebook.
I text message this morning and she was.
I prayed that school would close. I was like,
literally ending. I was like, actually, for
Judgment Day.
I
was like, and you know what's so crazy? So we call Judgment Day Layama, and then there's something called like the Layama prayer, and then it flashed on my phone. I was like, guys, oh my goodness,
I'm gonna rip that right now.
my mom was like, I kept turning off my lights thinking that school was gonna get canceled. Somewhere was gonna be a car crash today. I don't know. Mom and getting back home. I know it.
When did the storm end?
The storm ended around like 3 a.m. and then it started raining around 4:40 and then stopped raining and then rained at 5:30. I was up for the whole thing, 2.5 hours of sleep.
How are you late if,
Oh, we had to drop off my brother at school.
oh,
All right, I've used it earlier this semester.
What my bed at first.
Be there.
would it be less than like 0.0000 something?
All right, so I'm gonna shoot off memory on this one then, since I can't seem to find the bit that I'm looking for. All right, so usually, much less than is 10%. So if theta is less than 0.1, this is when it's appropriate to use. You are at 30 degrees, you're about 5% off. So it depends on how accurate you want to be. However, over here, we need to connect it up with this again. So we've got, dropping back. So we have this 2v sine phi. So what I want to do is, since I want to know the acceleration at a particular point, so let's say this spot here in the middle, if I want to know the acceleration here, I know it's in the negative j hat direction, I'm going to let phi get smaller and smaller. I'm not going to let it equal 0, I'm going to let it approach 0. So I'm going to make this incredibly tiny. And if I do that, then sine of phi here is just phi. So my acceleration, negative 2v sine phi over time, j hat. If phi is small, then this would be approximately equal to negative 2v phi over time, j hat. Or rearranging it, I'm just going to put that out front, negative j hat. I've got 2v over time, 2 phi v over time. Well, 2 phi is just this angle right here. that's 2 phi. And I know from the previous relationship that we had discussed, that should be equal to the arc length divided by the radius. So this is equal to negative j hat times the arc length, which I'll just label as S over time, times V. Sorry, try that again, S over R. S equals R theta, therefore theta equals S over R. Let's go ahead and label this. So the distance from here to here is S. So this is negative j hat S over time times V over R. And this S over T, this is the distance traveled divided by time, otherwise known as
Speed.
So we end up with negative j hat V squared over R. This is the acceleration of an object because it's changing direction. Alternatively, we also had that relationship that V is equal to omega R, so this is also negative j hat omega R squared over R, which is negative j hat omega squared R squared over R, which is negative j hat omega squared R. So, either one. Depends on what you're given. So if I have something that's traveling in a circle, the direction of, at a constant speed, the direction of his acceleration is towards the middle. Now, I had it in the negative j hat direction here because I picked a spot that was in the j hat direction. But if I'm over here, I can make that j hat direction. No matter where I am, it's always going to be pointing towards the center. So as I spin this around, there is a force that is pulling it towards the center of the circle. If it's horizontal, I'm the center of circle somewhere around here, not here where my hand is, it's here, somewhere around here. And there's a net force in that direction. If that's the direction of acceleration, that has to be the direction of the net force. That force is called the centripetal force. The acceleration it's experiencing is called centripetal acceleration. Questions to hear before I compare it to that other word, and hopefully the last time we ever use it.
What other word? Centrifugal?
Yep, that's the word. Any questions before we tackle the difference?
Yeah, I'm kind of hung up on the negative j hat times S over T times V divided by R.
Yep.
The numerator is S divided by R times V.
The numerator S divided by R, oh. So the intermediate step,
Yeah,
would be S divided by R times V over time.
okay, yeah. So if you're converting that to the next step, wouldn't you divide it all by V?
We're multiplying times V, why would we divide by V? Oh, you're
Yeah,
talking the
well-
second V.
Yeah, to get,
All right, so if you recall, dividing by a fraction, same as multiplying by the reciprocal.
yeah, that's
So
one.
S over R divided by time is S over R divided by time,
Yes,
which is S over R times 1 over time,
yes,
which is S over RT.
yes. So then how do you get V in that equation? That's still in the numerator, that's all alone? Basically?
Yeah, well,
Oh, okay,
the V is coming from there, coming from,
okay, thank you.
okay. Other questions?
Yeah, please don't erase that, by the way.
So, when you're talking about how negative j hat times 2 phi r divided by t is equal to the arc length minus the radius.
Arc length divided by the radius.
Yeah. What is, I don't quite understand that.
All right, we had. This is the point where we get the relationship between the angle and the arc length and the radius. Are you good with this? Good. Are you sure? I mean, you nodded, it wasn't convincing.
So it's SV divided by RT? Basically?
Yes.
Okay.
I guess I don't get how 2 phi was equal to s divided by r.
All right. Do you accept this? All right. This is the arc length, radius, angle. If I'm looking at my circle over here, I'm looking at an object going from this point to this point at a constant speed. So the arc length is the distance that it actually travels. That's s. My angle, I'm going from this angle to that angle. Well, I define phi to be from the central point to here and then central point to here. So 2 phi is the angle. So if s is equal to r theta, then s over r would equal theta, and theta is that angle that is associated with that arc length, which is 2 phi. Okay. Other questions?